Welcome everybody. Today we will start with a lesson of mass spectroscopy. Just keep in mind this technique or device helps us to identify the molar mass of any compound, and it helps us to understand and to know the framework of the compound. I mean, like how it looks like. Is it like branched? Is it a ketone? Is it an aldehyde or something? So in this lesson, we're going to learn the basics of the mass spectroscopy. Our simple compound is going to be a propane, CH3, CH2, and CH3. If we insert our compound in the mass spectroscopy instrument, the first thing that will happen, like a beam of electrons, high energetic electrons, will hit this compound. And as a result of that, this compound is going to be CH3, CH2, CH3 with a positive sign. And now, like, why do you have this positive sign? How can I represent it as a term of equation? Just keep in mind, as a result of hitting this compound by a high energetic beam of electrons, the one of electrons in this compound will be ejected. So it will be ejected in addition to this electron. So it's going to be like as an overall number of electrons of 2. And we have to represent this as an electron. So this high energetic beam of electron will hit this beautiful compound. As a result of that, this compound will eject an electron. The combination of this electron from this compound and this one here leads to the total number of electrons in here, in addition to this compound, which is, like it's positively charged. Now, this compound, as we can see, has a positive charge. And to be honest with you, this compound is unstable because it has a charge of positive 1, and then it will start to have a fragmentation thingy. I mean, like it will start to break. So this breaking, like since it's a fragmentation process, it's unpredictable. We could have a breaking like in this area in here, or a breaking in here, or like the whole thing with no breaking. First of all, since we have a whole compound with a positive charge, then it has a molar mass. The overall molar mass of this compound is equal to 44. How does this thing appear on a graph? First of all, if we use this instrument, we'll end up with a diagram, a mass spectrum. The x-axis represents the mass per charge ratio, or M per Z, and the y-axis represents the abundance, or like the amount of these fragments. As we mentioned before, we have a molar mass of 44, so it has a peak at 44 in here, and we sometimes just notice there's like a small peak like here, and appears at 45, or like a difference of 1. So this one represents the presence of isotope of carbon 13. So if you were also like about what we have, like what you have this small peak, it belongs to carbon 13. It has a very low abundance in nature, and that's why it appears as a very tiny or short peak. So just keep in mind this peak, which is on the right hand side, represents the molar mass of the compound. So this is the first piece of information that we can get from this compound. If this compound was breaking from here, like as a CH3, like just keep in mind CH3 is broken, it has a molar mass of 15. So you will notice that the presence of a small peak at 15. By the way, guys, this graph is roughly like drawn or something, so like just skip this point. And we could have a breaking of this peak from, let's say, from CH3, CH2. And if we calculate the mass of CH3, CH2, it's 29. So we possibly have another peak at 29. So if you were asked, like, what does the 15 mass to per charge ratio represent in a fragment, you have to say this one represents the CH3 positive. This one represents CH3, CH2 positive. This one represents the CH3, CH2, CH3 positive. And do not forget the positive. The positive side, it means that this fragment hits the detector of the mass spectrum, and because it's a charge, it's affected by the magnetic and electric fields, if you remember this. One more thing. If we have to write the equation of like the fragmentation process, we have CH3, CH2, CH3, and it was positive. Okay, just keep in mind if we have a fragmentation from here and the other thing in here, just keep in mind you should have two possible products. This one, the CH3 first, and CH2, CH3. One of them is going to be a radical, and one of them is going to be a positively charged species. So we could give this positive and this one here as a radical from the carbon side, or we could have a radical of CH3 and CH2, CH3 positive. So at that point, we will have a peak at 15 and another peak at 29. And there is no peak for these radicals because they are neutral, they have no charge, and that's why they're not affected by magnetic and electric field in the mass spectroscopy instrument. So if you were asking the exam, like how to write this equation, just keep in mind you have two species. One of these species is a radical, and one of these species is a positively charged species. In order to make the life easier, there is a good table to be memorized. I literally highly recommend you to like memorize these fragments because it helps you a lot to understand every single thing. If you have these two compounds like CH3, C double bond O, and CH3. And on the other hand, we have another compound, CH3, CH2, C double bond O, and H. If you just look at these two compounds, the first one is ketone and the second one is aldehyde. And if you count or calculate their molar masses, definitely they're equal. So the first one has a molar mass of 58 gram per mole, and the second one has a molar mass of 58 grams. So if you want to describe their or to draw like a very simple or approximate mass spectrum for everyone, let's call this one here A, the second one is B. Okay, the first thing that is common between them is both have a same molecular mass. So this one he's going to be like at 58 and this one he's going to be at 58. So we still have the same thing. But if we want to distinguish between the two compounds using a spectroscopy thingy, okay, let's go to the structures in here, first of all. Okay, this is the structure. We have a breaking from methyl group and the other guys. Okay, we have a breaking from this methyl group and the other guys in here. So technically, we have a same fragment at 15. So we're having a 15 fragment at CH3 in here, and we have another fragment. So we can say, okay, we have 15 right here, and okay, I'll put it like here. We have another 15 thingies right here. So till now, we have the same thingies. Now, what happened if we have a break from like this? Okay, if you just remember that these fragments could be memorized well, so you can say this belongs to this fragments belongs to this one, which is 43. So possibly in A, we could have another 43 fragment, which represents the CH3 CO positive, and this one here is for CH3 positive. This guy here is CH3 positive. If you look at B, we could have another fragment like this, which is, like CH3, CH2, and it's almost like this one here, which is 29. So this one is going to be 29. So possibly in B, we could have a fragment at 29. But if you look at this fragment in here, or this compound in A, it's so impossible to get a 29 like mass to per charge ratio in A, which means that I can distinguish between the two structures with the absence of a peak at 29 for A and the presence of the 29 peak at B. And finally, we could have like another peak from here, like this, which is also, if you calculate it, it's going to be 43. So you just notice that the only difference between these two structures is the absence of the 29 in A and the presence of the 29 mass per charge ratio for B. So this is a way how to distinguish between these two structures. I just want to remind you with other thing. If you just remember from like the previous semester, that we have two possible isotopes like chlorine and bromine. And we said that the chlorine atom has two main isotopes. We have chlorine 35 and chlorine 37. And for bromine, we have Br 79 and another one which is Br 81. The ratio or the natural abundance of the chlorine 35 to 37 is a 3 to 1, which means it's greater like in amount, but for bromine it has a 1 to 1 ratio. If we have, for example, like just keep in mind, if we have, let's say, CH3, CH2, C double bond O, and we have Cl, um, like what are the possible fragments for this reaction? Okay, the first fragment, it could be CH3, which is 15. Okay, we could have another fragment appears at CH3, CH2, which is 29. Okay, and we could have a fragment like from here, like this. So we have two possible fragments for this one here. If you count the carbon like as a molar mass for chlorine when it's like 35 and when it's 37, if you count the C double bond O, you can say like we have 16 plus 12 plus 35, or 16, 12, and 37. And if you count them, let me calculate them in calculator. So the first one is 65 and the second one is 63. So if we have a fragmentation, like a possible fragmentation for this one, it's going to be like this. Okay, first possible fragment is 15. Okay, the second possible fragment is going to be at 29, and we have two possible fragments, and just keep in mind the ratio is 3 to 1, which means that the peak at 63 is 3 times greater than the peak at 65. You can see, so this fragment represents COCl, and just keep in mind this is 35, this is CO, don't forget the positive sign, COCl37, and this is a positive sign which represents, the differentiations between them. And if you do the same procedures, but if you change this atom to bromine atom, it's going to be the same thing. Okay, we could have a fragment at 15 and another fragment at 29, and two fragments, but they have the same height for bromine. And if you just remember that if we want to calculate the molar masses of bromine atoms in the whole compound, 16 plus 12 plus 79, you will have a peak at 17 and another peak at 109. Okay, just keep in mind the two peaks for the bromine are like, have the same heights, but they're different, and like the chlorine when it's a 3 to 1 ratio. Okay, now let's practice this question. We have a mass spectrum, we can see, and we have a possible corresponding compound for this spectrum. So how can we deduce that? You just notice that if you look at the peak in here, it has a molar mass of, this is 55, 56, 57, 58. So the molar mass of this compound is 58. So the first thing that you have to look at here is which of these compounds has a molar mass of 58. If we calculate the molar mass for the first compound, we have 12 plus 3 plus 12 plus 16 plus 16 plus 1, it's equals to 60. Okay, so we ignore the first answer. And if we count this one here, it's 12 plus 3 plus 12 plus 16 plus 12 plus 3. And if you apply that in your calculator, you'll end up with 58. So this question here, technically, so far it's a possible answer. And if you count the same thing down below in here, it's equal to 58. So how can I distinguish between B and C since they have the same molecular mass? We could have a possible fragment at CH3 and CH3, so we possibly have a peak at 15. And another peak appears at, oh, look at here, this is 40, 41, 42, this is 43. So we have a peak at 43. But, like if we have a fragment for C, we possibly have another peak at 29, and there is no peak at 29 in here. So technically we can exclude C at this point. It's not the answer. And just B is your answer. You will wonder like, okay, if we calculate the molar mass of this compound, it has a molar mass of 58. But why it's not the answer? Because if we have a breaking for this compound, we should have a peak at 15 and another peak at 29 and another peak at 43 and another peak. Yeah. So there is no peak at 29 in D. There is no peak at 29 in C. So definitely the answer is B. In B, because it has a 15, this is for CH3 and this is for CH3 C double bond O positive, and this is for the whole compound. So the answer is B in this case. And if we think about this question too, it looks like the same one. It's 15, which means that we have a fragment. All of these guys have a fragment at 15. Okay, so we have another fragment at 43 and another fragment at 85. So definitely, if you have a good mindset, if you have a good memory about this peak, it's going to be CH3CO positive. And if we combine it with CH3 positive, you will end up with this one in here. So the answer is also B in this case. So it says, which of the following carboxylic acids would be expected to have a major peak in its mass spectrum? A major peak, it doesn't mean like the M plus one or the last peak. It tells you that like one of its peaks, one of the fragments, a major peak, like the one which is the tallest one, the tallest peak. I just want to let you know something about the peak as well. Okay, since we have this peak in here, we have this guy, and we have these guys in here, we can say that this one here, which is M plus 1, which is the one that tells me about the molar mass, is called molecular ion peak. Molecular ion peak. And the tallest peak is called the base peak, and it's the most stable. Okay, the most stable fragment. Okay, so this does like it tells me a lot. Now in this graph or mass spectrum, we're gonna say like which of these structures can give us a possible like fragment at 57. I just want to give you the final answer in this case because we're gonna do like repetitive work. So I just want to give you the idea of this one here since you like don't waste a lot of time in that. If we take the last one, which is the correct answer, and say like CH3, CH2, C double bond O, OH. If you start taking the fragment in here, it's 15. And if you take it from here, it's 29. And if you take it from here, I mean like the whole thing like this, if you want to calculate it, you have a carbon, which is a 12, plus hydrogen, 3 hydrogen, plus carbon, 12, plus 2 hydrogens, plus 12, plus 16. If you count all of these guys, all of these fragments together, you will end up with a fragment of 57. And if you tried the same procedure for other compounds in here, you never have a fragment with a mass per charge ratio of 57. So if you want to write it, it's going to be like this. This fragment is CH3, CH2CO positive. So the molar mass of this compound here, or the molar mass of this fragment is 57.